Good evening. You are welcome to this class, Chem 205. Last week we tried to look at, look at group 3, that is the carbon group. We tried to look at the composition of the group, and we also tried to look at some of the properties of the group. We look at carbon in particular, and we said carbon, being the first member of the group, is the smallest member of the group, and it has some peculiarity in behavior which differs from other members of the group. We also try to look at the fact that there are two allotropes of carbon graphite and carbon diamond. And we say the carbon graphite, which is soft, and the carbon diamond, which is hard, the structure. Today we are going to be looking at the chemical properties and some of the physical properties of this group. I wish to share with us some of these properties as can be seen in the slide that we have before us, particularly in the physical and the chemical properties of the group. As we've said earlier, that you must have noticed that in group 13, that in the P block elements, they show some kind of stable oxidation states. And the elements of the group 4, their most common oxidation state are +2 and +4, which are also the valencies, except for carbon, where oxidation state varies from -4 to +4. However, the valency and the stable oxidation state for given elements sometimes may differ. Valency, as you know, can be defined as the combining capacity of an element, or maybe the number of electrons that is lost or gained or shared in the process of bond formation. Oxidation state or oxidation number, on the other hand, is equal to the charge the atom could have if all the elements in a covalent bond is formed were assigned to the more electronegative atom that are actually in the bond. And there are rules that accompany this. That is the assignment or the deduction of the oxidation states. You can see in the slide before you that if they are in combined state, the oxidation state is -0. While if they are in combined state, X, except for the peroxides, the oxidation state is 2. In peroxide, it is -1, while if they are combined with hydrogen in the hydrides, it is +1. If they are combined with hydrogen in the hydrides, is -1, while if they combine with, except for the hydride, is +1. The alkali metals in group 1, they are +1, and the alkali earth metals, they are +2. And as we are also aware, the sum of all the oxidation state is +2. We'll also be looking at the chemical properties of group 4, their chemical reactivity, which increases down the group. Under this, we'll be looking at the carbides, the halides, the fluorocarbons, the hydrides, and the oxides. The carbides, e.g. carbon linked to other elements of lower or approximately equal electronegativity. There are binary compounds are called carbides, like calcium carbide, aluminum carbide, and barytes. Calcium carbide in particular, if we go back to the slides that we have before us, you see some of the properties as shown down on the elements in the periodic table. Sorry, some of those things, I think they are not properly placed. Let me still go back to what I have there. So the carbides, you have like calcium carbide. Calcium carbide is actually an important compound, which mostly we use for welding, because when calcium carbide reacts with water, acetylene gas is actually produced. If it is aluminum carbide, methane gas is produced. This aluminum gas and methane gas are actually very, very important in the field of chemistry. They are salt-like or ionic carbides, and some of them can be ancestral carbides or covalent carbides. In ionic carbides, the elements of group 1, 2, 3, 11, 12, or 13, except for boron, they try to form ionic carbides. And these ionic carbides are also very important compounds that we use in our day-to-day activities. They are mostly colorless, they are non-conducting in their solid state, and they are decomposed by water or dilute acids. Take, for example, carbon tetrachloride. Carbon tetrachloride does not react with water, but silicon tetrachloride fumes in air because the availability of the orbitals in silicon metals can be able to accommodate some other donor groups that may come like HCl. And that's why if silicon tetrachloride is exposed, it can easily be hydrolyzed, while the carbon components will not be able to do that. If we look at the covalent carbides, the covalent carbides are formed by a combination of carbon with elements of almost equal electronegativity, like boron or silicon. An example is silicon carbide or boron carbide. The boron carbide is a giant macromolecule and is also very useful in the field of chemistry. They are hard, they are infeasible, and they are chemically stable. Boron carbide is even harder than silicon carbide, and it is an abrasive. It's mostly used as abrasive in most industries. The halides, all elements of the group form dihalides, except for they form dihalides except for the tetrahalides. The fluorides, the chlorides, the bromides, and the iodides are known for all the elements of the group, except lead tetrabromide and lead tetraiodide. The lead tetrabromide and lead tetraiodide, since lead is a very heavy metals, mostly its formation with these elements is very hard. And the tetrahalides are volatile for the covalent compounds. An example is what I gave you said earlier in silicon tetrachloride. It can easily fumes in air or react with water to give you salicylic acid, and HCl is produced at the end of the day. The tetrahalides of carbon are inert to hydrolysis, while that of lead and tin undergo incomplete reaction. They cannot be able to completely decompose. But that of silicon and germanium can easily be hydrolyzed. That of carbon completely, they cannot be hydrolyzed at all. The fluorides or the fluorocarbons, these are synthetic equivalents of the hydrocarbons. Fluorocarbons are synthetic equivalents of the fluorocarbons. Uh, Fatima, you are joining me? Hello? Can Fatima hear me? Hello, Fatima. Hello, are you with me? Okay, I will continue. Once you are through, say hi to me so that we can have a good interaction. I can ask you some questions and you may also be able to ask me some questions. But so far, I'm going to continue from where I stopped. Maybe later or by tomorrow, you will be able to read this thing. Yes, peace, you're also welcome. Can you hear me? Peace, can you hear me? Okay, I'm talking about the fluorocarbons. And I said that these are synthetic equivalents of the hydrocarbons, in which some or all of the hydrogens have been replaced by fluorine atoms. If there was a board, I would have tried to make the illustration to you how the carbon atom is able to accommodate some other incoming ligands that would want to bind themselves to it. Like we said in our previous class, that carbon has 4 electrons in its atomos shell. So there is a tendency that carbon will require more other electrons in order to attain an octet configuration, or carbon giving out 4 electrons in order to attain an octet configuration. But as a result of that, it's easier for it to get electrons from donor atoms. So carbon would in case engage in sharing of electrons with other atoms that are actually present. So it can be able to form elements with hydrogen atoms that are attached to it. It's also able to form compound with fluorine atoms that are also attached to it. So you can have carbon tetrafluoride or dicarbon tetrafluoride. And like hydrocarbons, the fluorocarbons are capable of forming carbon chains. I'm sure we talked about catenation in our first class. Catenation, we said, is the ability of an element to form a long chain with itself or with other atoms around itself. So carbon linked up with fluorine is also possible for it to form a long chain of other atoms of fluorine or chloride attached to it. Carbon tetrafluoride is the simplest fluorocarbon and it is a colorless gas and is mostly available and used around. The next property is the oxides. All elements of the group, they form anions or monooxide or dioxide. They form monooxide or dioxide. The monooxide are examples like carbon monoxide, And you can have dioxides, that is the carbon dioxide. The dioxides are thermally stable except for lead dioxide due to increased instability of +2 oxidation state down the group. That's why they are able to form that stable oxide. They also have acidic character or acidic behavior. The acidic character of the dioxide decreases also down the group. Now, if you have the carbon, which reacts with steam, or when carbon is passed over red hot steam, it's going to produce carbon monoxide plus hydrogen gas. This is normally referred to as water gas, and it's a common reaction that takes place. The next you can have is maybe calcium carbonate reacting with HCl to give you calcium chloride with water and carbon dioxide. So we discovered that it's a very important compound for the production of some other things like carbon dioxide or some other carbonates that are needed around. It also forms complexes. They can form complexes, but carbon cannot be able to form complexes. The reason is that complex formation requires the attachment of a ligand to the central metal ion. Now, if the central metal ion here is carbon, after it has combined itself with other this thing, it stops at the p orbital. There is no availability of d orbital in carbon. So once carbon binds itself with other elements like either chlorine or fluorine, thereby forming either carbon tetrachloride or carbon tetrafluoride, all the available orbitals in carbon are properly bonded, and therefore any other incoming ligand cannot be able to find a space to attach itself. Now, but other members of the group from silicon, germanium, tin, and lead, all of them have availability of d orbitals. Now, because of the availability of d orbitals, there is tendency for them to receive donors, that is ligands, that will donate lone pairs of electrons into those available d orbitals, thereby forming a complex with other compounds that are attached to a cell. So they are important. All these compounds, these reagents, we talked about them, they are very, very important, and they are also very, very useful in the course of chemistry. For now, let's enter into some interaction or some discussion, and let me hear some of maybe the complaints that you may have to see how we can have a proper time, because you people are 21 in the class, and so far, the first class I had, I think it was only Fatima that attended. Today, I've had Peace near Barry. So maybe we don't know. Is it the time that is not convenient or whatever? Are you listening to me? Can you hear me?
Maybe, probably they didn't know that there is a class.
But I sent this notice since on Monday. When did you get the notice?
I can't really see. I think it's Monday. Yes,
Yeah,
I think it's Monday. Yes.
I sent the notice since Monday because the other one I thought because it was impromptu, maybe that's why a lot of them didn't attend. But this one I decided to send it very early enough so that people can have time to attend. And I did also make it in the night time so that it can be in the daytime that may be convenient. So is peace with us? Peace, can you hear us? Please, can you hear us? Now, Fatima, are you with me?
Yes, sir.
Can you tinker around? What are the most important uses of some of the carbon compounds, like example, carbon dioxide?
Carbon dioxide.
Yes.
It's used for use it in I mean, it's used for a gas. I mean, in the air now.
Eh?
Carbon dioxide.
Carbon dioxide,
It's for, I think, fire extinguisher.
of course, is used sometimes in some fire extinguishers, but the most commonest use is that is the available gas that plants use for photosynthesis.
Gas, yes, that's used for, yes, for this
They use
test.
for photosynthesis, yes. So the plants take carbon dioxide to manufacture their food and in turn return back oxygen. That's why they also serve as actually air cleaner. They take up the carbon dioxide, which also adds to the global warming because it's one of the greenhouse gases. Carbon dioxide is one of the greenhouse gases that add to carbon warming. So plants take up this carbon dioxide to manufacture their own food and thereby releases oxygen, which animals and humans also require for their own
Also
survival.
breathing.
Yes. So can you remember I told you last week about calcium carbide?
Calcium carbide.
Calcium carbide.
Ah, I
I,
can't remember.
I told you last week calcium carbide, that is CaC2,
See, CAC2.
that in the presence of water, acetylene gas is produced, and this acetylene gas is what
And calcium oxide.
welders use for welding. That is what they use for welding, the
That?
acetylene gas. Yes?
Okay.
I said they use acetylene gas for welding.
Okay, well then, yes, I remember.
Yes, yes, yes.
I've forgotten it.
So do you have any question you want to ask me?
Bye.
Do you have any question you want to ask me? Okay.
Actually, I came late though. I think I didn't have light on my phone, so I need to borrow phone to come to class. So I came late. I don't know what you have done so far. Just met you on complex formation.
Hello, sir. Good afternoon, sir.
Yes, please, how are you? Hello?
I'm fine, thank you, sir.
You also
Yeah,
came
hello, fine, sir. I'm fine, sir. Thank you, sir.
you also came late into the class.
Yes, I came late. I'm sorry, sir.
What is the problem?
Yes, this is my first time of attending the class.
How did you get to know about the
I
class?
went to somewhere and I came back late.
You went
I not checked yesterday on the e-learn space and
and
I saw that we were having class by 3 p.m. today.
okay, did
I
where
never joined. Sir, what I want to ask,
yes?
please, sir, how can I access the other classes that I have missed?
I uploaded it on the this thing. Did you check the recorded this thing on the learning environment?
Yeah, he's there.
Fatima is showing
Okay,
there.
okay.
So please check the
Yes,
learning
Okay.
sir, yes,
environment
sir.
in the recording, you will see it there.
Okay, thank you, sir.
Yes, thank you very much. I think we may have to stop the class here until I will fix another one the same time next week again. Are you with me?
Yes, sir.
Yes, let's meet the same time next week.
Okay,
Next week. Okay, sir.
by 3 p.m., right?
Yes, by 3 p.m. Thank you.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Yeah.